Right. So let me define here an arbitrary intersection union. The intersection this is the set of X such that X is in AI for all I in gamma. That's a little bit intuitively. Let me say it. Let me say it absolutely formally. More formally, what does it mean to live in this intersection here? X is in the intersection of AI if and only if for all X and implicitly what I mean here is for all X in whatever my universe is, wherever we're living. I is in gamma implies Xi. X. So what it means to live here is for every, if and only if X lives here, if X for all I, for every I in the index set, X has to live in AI. So what it means to live in an intersection is for every one of these sets, X has to live in it. Two, what is a union? To live in a union, you only need to live in one of the states, right? Again, more formally, X is in union if and only if, this time not for all I, X lives in AI, but for some I. So there exists I, such that I is in gamma and X is in AI. So let me give you some examples. So how many of you are a little bit confused about this indexing stuff thing? It's a little bit off. Let me give you some simple examples. Suppose I just have two sets here, right? Does everybody feel comfortable with what the union of those two and the intersection of those two are? Here, my indexing set is just the two numbers 1 and 2. That's it. So what the indexing set is this allows me to intersect a large number, perhaps, of sets, right? Instead of just going A1 intersect A2, this might be over big. And you've probably seen some stuff like this too. Let me give you an example. Here's an infinite family of sets that I might want to intersect for you. Right? I1 is the interval from 0 to 1. Right? I2 is the interval from 0 to 1/2. In is the interval from 0 to 1/n. Forever and ever. But so if I wanted to intersect all these, I might write this way. Have y'all ever seen notation that looks like that, perhaps? Right? You've probably seen it in Calc 2, where instead of an intersection sign, you had a sum, right? Anybody want to guess what this is? Here, my indexing set, here, gamma is the natural number, right? Start at 1, 2, 3, all the way forever and ever.
Would this be the intersection of all of these sets I
Right. And so anybody want to guess what this intersection is?
0, 1, that interval? No, no, 0.
It's just only the number 0 is in every one of these intervals, right? Would everybody agree that 0 is in the intersection? Because it's in every one of these. Agree? And that's what it means to live in an intersection. Can somebody give me an argument that nothing other than 0 is in here? Let's prove this. I'm trying to show two sets of the same thing. This big intersection and just this, the number 0. How do I show the two sets are the same? Well, I have to show contain both ways. No. We're all in the natural numbers. 0 is in the interval from 0 to 1/n. So 0 is in IN for all in natural number. So 0 is in intersection. Everybody okay with that? Now, the interesting part is why is that? Why is that always there? Yeah.
I just have like a general thought. Could you look at the complements of all of I and realize that complements have 0?
Well, yeah, complements in what?
Complement of the set I and.
The complement in what? Because when you tell me a complement, you have to live in some big universe. But these are reals. These are intervals from 0. So for example, 1/2, right? These are right. So you could do something like that, I'm sure. How about the other approach? Now suppose there exists X in X. No, see. Anybody you can tell me why this can't be? You actually use this on one of your homeworks. Does anybody remember the Archimedean principle? There are many, many ways to state the Archimedean principle, but since X equals not 0 and X is in IN for all n, X is a positive real number. Do I agree with that? So there exists a capital N in the natural numbers such that X such that one over n is less than x. This is the Archimedes. Which you used in a previous one. So what does this mean? If x is bigger than one over n, then what does that mean? That x cannot be an I sub n, which is the interval from 0 to 1 over n. Because x is too big to be in that interval. Right. But if, what's that mean?
Fine.
So x, oh,
Okay. I was,
not in, absolutely. X is not in, right, because x is too big to be in. So x is not in the intersection of I, yeah. And this is a contradiction because we assume that x was in the intersection. So we've shown that this is exactly. Okay, any questions on that? You can have even bigger index sets, for example. This is going to be, this is kind of silly, but it illustrates my point, I think. Um, so let's do this way. Okay, this is kind of silly. I'm going to define a set, a sub I, just to be x sub I, where x sub I is just the number I in the real numbers. The real numbers is the union so x sub 1 is 1, x sub 2 is 2, x sub square root of 2 is the index x sub square root of 2, x sub pi is I equals pi, and this is the union of AI. This is a very large index set. So see, I'm indexing these by the or I'm sorry, by the real numbers. And so I have to write it in this form because we're going to get to this later, but unlike the natural numbers that you can list in order, 1, 2, 3, 4, 5, you can list those in order. You cannot list the reals in order like this, which was what requires the strength notation that I have here. Okay. Okay, so proposition 228. Suppose the gamma is a family of sets, B is an element of this family, then the following hold. Okay, so what does it mean for B? So gamma is a family of sets. B is in gamma. That means B itself is a set. Right. Number one, intersection of A Why is this? Well, let me kind of talk you through this. This is intersecting all the sets in this collection of sets, right? B is one of them, right? So the intersection of all of these, B is part of this intersection, so this is contained in B. And there's a similar kind of out the other side. B is contained in the union. The same sort of argument holds here because B is one of the elements of the set. So when you union them all, B is contained in there. And here's a little strange one. 3. If gamma is not empty, then the intersection of contained in the union. Not a surprise, the intersection of a bunch of sets is contained in the union. But why did I say that gamma is not empty? This requires a bit of logic. So let's look at this for a moment. Ask you this, what happens if you union a bunch of sets? This is kind of logic, let's try to think about this. What happens if you do an empty union of sets? One would think, and that is in fact correct. Right, everybody agree with that? If I union sort of nothing, I should get nothing in a certain sense of the word. And let's look at this. What does it mean for X to live in AI? There exists an I in gamma. Oh, there's no gamma, or there's no I in gamma, right? So everybody kind of cool with this? That the empty union. How about this? Empty set, right? It's the universe. That's totally bizarre, isn't it? Can anybody explain why that's true? How can I do an empty intersection and get the entire universe? Am I on drugs? What's going on here? Let's look formally at this. What does it mean for X to live in this intersection? For every I in gamma implies X is in AI. What is true about this statement? If gamma is empty, it's if gamma is empty, what is true about I and gamma? It is always false, right? And what is true when you have the implication error? F implies, doesn't matter what this is always true. So if gamma is empty, this is always true. So every X in the universe is in the intersection. This is a little bit counterintuitive and it's sort of more fundamental logic, right? Most intersections, when you intersect them over a non-empty set, you get exactly what you expect, the stuff that's in all of them. When you have an empty intersection, you've got this strange thing with the intersection. Everybody see why this is true. To live in the intersection, this is true if and only if the statement's true. But if gamma is empty, the statement is always true. So everything in the universe lives in the empty intersection. And that will be an important thing about me asking you and picking on you earlier a little bit about, okay, what's your universe? Right? Because if you're this will turn out to be whatever your universe is. specified problem. Okay, any questions on that? Okay, let me give you a theorem. Some of this you actually show in your homework. Let AI be a collection of sets. Uh, Sets. So we have the following, the intersection. Okay, beta for all beta and gamma. The union, well, I'll write it this way. Three. Here's kind of the big. The next two are kind of the Morgan's laws. These are generalizations of what we did before. If you look at the intersection, gamma. What do you suppose this is? When I union, this is intersection of AI comma. So you prove this last two, which are the interesting ones in your homework. By the way, here's another kind of tie together. Do you all still think it's a little weird that when you take an empty intersection of sets, you get the whole universe? But you can see it right here. Are you all more comfortable if you take a union of nothing, you get nothing, right? So here, this would be the empty set, if that's an empty index set. The union of a bunch of no union of sets is the empty set, right? What's the complement of the empty set? The universe, which is okay. I am going to give you this one last definition, and then we're going to get started on one of the coolest things. We're going to use this especially later when we start counting or getting serious about counting. We say family of sets. We'll call it A I. Is pairwise disjoint. If, by the way, I hate doing this, but I'm going to do it anyway. I mean, this is almost like what am I thinking? What do you think might be a good definition for pairwise disjoint sets? What's that? Well, that's what I'm asking you guys. What does it sound like?
It's like set over here, a set over here, it's like empty spaces.
That's very intuitive. That's very good. So let's see if we can turn that into. Basically, what he said is any two of them don't overlap, right? So let's do that. I want any pair of them to not overlap. So if they're not the same, AI intersect AJ is equal to the empty set. If I and J are different. So if these are two different indices, then the sets don't overlap at all. Pairwise disjoint sets we're going to study later because they make it easy to count, right? Okay. So here's a question for you. How many of you have ever heard of induction? And this is not what they do to you in the military, right? This is a mathematical thing, right? How many of you have heard of Sherlock Holmes? Ever? What's he famous for? He is famous for deduction, right? He figures out crazy crap from, just these small little clues, and he deduces by throwing things out. Induction is sort of, you build a ladder, right? And that's what we're going to do here. And let me show you a pattern that might be a little frustrating for you. Nine. 16. You might see a pattern here. They're all squares. Looks like they're all squares, doesn't it? Is this always the case? Probably. Yeah, it seems probable. Right? However, here's the bad news about math. I can come up with patterns that will work for the first 2 billion terms. Just give me a number. You want how bad you want it to be? 2 billion terms. I can give you something that will exhibit what looks like a pattern of 2 billion terms, and then starts to screw up at the 2 billion first term. So how do we really know? It looks like they're square. How do we show this? This seems like a very kind of daunting problem when you really think about it, because I'm asking to show in general that the sum of consecutive odd numbers turns out to be a square, right? And there's infinitely many. I can go on forever with this, right? How do I begin to prove that infinitely many things work? Well, this is basically at the heart of what we call induction. Before we can do that, though, we need to start out with some basic properties of the natural numbers. Because natural numbers, well, or the equivalent of natural numbers, is where we can do induction. So I'm going to give you some of these properties without proof, and you will thank me later. How many of you have heard of Bertrand Russell? Some of you. And Russell and Whitehead, in an attempt just past the turn of the 20th century to set mathematics on its solid concrete footing, wrote a book called Principia Mathematica. It was several volumes. And this was their attempt to really put mathematics on solid ground. I have some of the volumes of that set, and the first one in particular, it is not a page turner, right? This is not something you want to cuddle up with and read in bed at night. I mean, it reads like wallpaper. There's logic symbols everywhere. It's awful. They take the first 362 pages of the book and prove that 1 + 1 is 2. Right. So we are not going to go anywhere into those kind of weeds here. We're going to take some of these natural properties, the natural numbers, and see if I can spell successor properties. just kind of reveal these properties that we will take as a given. Number one, first property is one is a natural number. That's not too hard to buy. Two, every natural number has a unique successor. Let me call some N as a so one's natural successor is 1 + 1, just what we call two. Two's unique successor is 3, so, right? Every natural number has a unique predecessor, with one exception. What is that?
Zero.
One. The right spirit, the natural number one has no predecessor. Right. I'll write that down. One is the unique natural number. That is not a successor. Another. These first three called successor properties. Basically, what they do is it's sort of like the sergeant calling out the natural numbers and making them get in a line. Right? Okay, one's there, you're standing first. Every one has a unique successor, two has a unique successor, three has a unique successor, and this goes on forever because all of them have that. And the last one just says one's the smallest one. Basically it. We have closure properties. One for all n, m, and natural numbers. N plus m and n times m in natural numbers. So that is to say, you can add two natural numbers, you get a natural number. You can multiply two natural numbers and you get a natural number. We also have, and I'm willing to bet that at some point, you probably yawned at this, but you've seen it before. I'm gonna call this associativity. For all n, m, k in the natural numbers, n plus m plus k is equal to n plus m plus k, and n in k equals n m. And these are things that you probably are familiar with. You've certainly used them before, just in doing ordinary computations. This is not linear algebra, so multiplication doesn't make any difference as far as order. Both addition and multiplication, it doesn't matter what order you do it, you get the same result. You have distributivity. So far, we've done these properties with multiplication and addition playing separately, right? We talked about addition, multiplication, addition, multiplication, multiplication, addition. Distributed property tells you, what they play. Nice. But this way as well. Somebody explain to me why that's superfluous.
Probably, it's gonna be.
That's exactly right. This one is, what I've written here is true. But once you know this, if you know commutativity, you don't even need to write this. Because this plus commutativity will give you this. So it's a little bit extra. And finally, you have the cancellation properties. Again, I'm gonna have NMK natural numbers. Number one, if n plus k equals m plus k, then in m and two, if nk equals nk, then n equals n. Okay, so let me ask you another fun question. Somebody earlier in this class, not today, but somebody had asked me, oh, do you count zero as a natural number or not? And no, I don't. And when I do n sub zero, that means the natural number zero thrown in. Given the properties that I've given you of the natural numbers, somebody explained my cancellation means that zero can't be a natural number. I can't have zero in the natural number set. Of course, if zero were a natural number, then I would have to change this to zero, right? But what goes wrong here? And yeah,
If K is equals to 0, then I don't know if it could be any other.
right, can't cancel anymore because I think we would all have to agree that 2 times 0 equals 3 times 0. But you can't just cancel the 0 and say 2 equals 3, right? So we don't want 0 here for the cancellation property. Okay, now I'm going to give you the principle of mathematical induction. So in this essence, I'm going to tell you everything that you need to know about induction. Now, that's being a little bit facetious, and I would be a real jerk if I didn't do a lot of examples, which we are going to do a lot of examples. But it's important that you know this. So here is the logical principle of mathematical induction. And maybe we'll try to prove this bit about the squares. Principle of mathematical induction. Let S in natural numbers be a subset with property. Number one is in the subset. So whatever the subset is, it's got one. It's not empty, it's got one in it. And if n is in S, then n plus one is in S. What does common sense tell you here? I have this mystery subset of the natural numbers. And I know two things about it. It has one in it. And whenever it has any natural number in it, it has the next natural number. It has to be everything. That's right. That seems silly, doesn't it? Right, me writing down an obvious statement. But this is the way that induction works. And it proves things for infinitely large sets, right? The first step right here, property one, is bottom rung of the ladder. And this, baby, this is the stairway to heaven, because it says if you've got any rung, you got the next rung. And so now if you've got this rung, you've got n plus 2 and so forth. So here's an example. Through that. Anybody want to guess what one is? Four, one plus three plus five, plus 9, 1 plus 3 plus 5, 7 equals 16. Anybody want to guess this here? Actually, you want it to be in square then, do you? How about that? Because, for example, when you go up to 3, that would be n is 2. When you want to go up to 5, that would be n is 3. When you want to go up to 7, that'd be n is 16 or something, right? But let's prove this. If I'm wrong, then this is a problem. Notice that I've got infinitely many problems here, right? One for each positive end. What is the smallest end in which this makes sense? This formula here. N equals 1. Everybody agree with that? That's the smallest one. Bottom right on the ladder. Well, 1 plus 3 plus 5 plus 2n minus 1 is equal to just 1, right? Because that sucker tells you where to end, and it ends at 1, right? And n squared is 1 squared, which is 1. So, formula works. Okay, with that? Now to finish this off, suppose this works for n equals m, show it continues to work. So here's what we've got. This is what is called our inductive hypothesis. Right, okay. Yeah, if you've got a fleet, go. I will finish this right there on the recording. This is the end case. What is the next step? See what I did? Said the same thing. This is the next term right here. And what is this to come over here? N squared plus 2m plus 1. So I say how to rewrite that? So the formula works when I replace m with m plus 1. There's your first inductive proof. Think about that and we'll go over that in more detail next time. Any questions?